definitions also. We have, you must know what is an eigenvalue, or how to find an eigenvalue, which in this case it will be denoted by the lambda. Next thing, we should be able to find the eigenvector, or we should know what is an eigenvector. So far we have been working with the coordinate vectors, so it won't be difficult for us to know what is an eigenvector. So since we've been working with the coordinate vectors, right? Now we need to know what is a characteristic polynomial. This is just an equation which we remember when we talk about polynomials, where we do not let's say we have ax squared plus bx plus c of the highest degree 2, at least at most 2, right? Or at most 2, yeah, let me say at most 2. So when we come to this characteristic polynomial, now we're going to be replacing this by lambda. This is where we'll be looking at lambda. We say that this equation, which is equals to 0, is a characteristic polynomial. And how do we find that equation? We find that equation by doing the determinant of a minus lambda I, which is the identity matrix, right? Now, after finding all these, we'll be looking at we'll need to know what is an algebraic multiplicity. Or in other words, let's say we have more than one or repetitive eigenvalue. Let's say we have something like this, -1 all squared, where you get lambda equals 1 and lambda equals 1. You say, right? So the multiplicity here will be 2, right? So in other words, we're having the same eigenvalue. Now, when we come and look at the geometric multiplicity, these two are going to assist us in making a decision, or taking a decision to decide, or you're going to decide whether a certain matrix is diagonalizable or not. We're going to be using mostly these two, or sometimes we'll be looking at the independency of that system. Is it linearly independent or not, right? So we'll be looking at all those parts. So when you look at these definitions, mostly, okay, let me just look at the definition and say, they say that a scalar lambda such that T of V is equal to lambda V. So this is not our first time talking about some transformation, T of V. We're talking about the transformation, that the transformation will be equal to lambda times the eigenvector for some non-zero vector element of V. So we know that an eigenvector, sometimes it's possible for you to look for an eigenvector and then you find 0, 0. But you should know that there is no eigenvector that should be 0, 0. So if you find an eigenvector that is 0, 0, this you must know that that eigen, or those values are not going to be considered to be a valid eigenvector. You say, right? So I think I did include some question here where when we look for the eigen vector, we find 0, 0. So you should know that. Now, and we remember this, that when we talk about a linear map from V to V, given that the domain and the codomain are equal, we call this a linear operator. So I think I should have written here a linear operator, but I just wrote a linear map because I realized that most people are used to linear map, right? So we call this linear map a linear operator, right? Now, let me erase this. Then, now when we come to the key properties, remember I said that we're going to be looking at things like linearly independency, we look at geometric multiplicity and algebraic multiplicity, right? If we look at this, they say that an eigenvectors corresponding to distinct eigenvalues, eigenvectors corresponding to distinct, is that right, or different eigenvalues are linearly independent. So we'll be looking at that. Let's say I have two eigenvalues. It means that each of that eigenvalue should correspond to its own eigenvector. Then that will be linearly independent. If I have two different or two distinct eigenvalues and they give me the same eigenvector, you must know that that thing is not linearly independent. Hence, it will affect the matrix from being diagonalizable, right? Now they come and say T is diagonalizable if there exists a basis of V consisting of eigenvectors. So you know a basis. What is a basis? So in this case, we know that a basis will be a subspace of V, right? And then if it consists of eigenvectors, in other words, let's say if I'm talking about a basis B, and then I have two eigenvectors. Those eigenvectors, if they're inside, therefore, we'll know that T is diagonalizable. So we'll look at that. But first, this first condition should be applied. Now, the third condition, so remember all these three conditions are going to be used for us to check. Sometimes our reasoning will be based on this, sometimes the reasoning will be based on this, sometimes this one, but mostly I want us to focus on these two, right? This one we'll look at it when we have some sort of multiplicity, you see, right? And then we'll look at this one. So let me try to erase this. But I wanted to focus more on the examples, but I realize that it's very important for me to explain this part, because it's possible that there may be some that haven't looked at the slides, right? Because people are on recess. So the last point says that for an n by n matrix, remember here where we're dealing with this one's non-invertible determinants, where the determinant is equal to 0. So since we're dealing with determinants, we're always going to be talking about a square matrix. You see, right? And they say that for a square matrix, T is diagonalizable if it has n linearly independent eigenvectors. Let's say this is a 2 by 2 matrix. We'll see our reasoning sometimes will be based on this. If this is a 2 by 2 matrix and we have two eigenvalues which each have its own eigenvalue, then this thing will be diagonalizable. This is what they're saying here. So it's also going to take us back to this part. You see, right? So this part, it's this one. Then if this, given that this is a 2 by 2 matrix and this holds, then we'll know that this matrix is diagonalizable. Right? Now, for the theorems, they say that if A is a triangular, upper or lower, its eigenvalues are the diagonal entries. So we'll look at this one if you come across such, but always, so mostly we're gonna be using this this condition. I'll show you when you're looking for the eigenvalues or eigenvectors. Now the sum of the eigenvalues equals to the trace of A. Remember, the trace of A is when I'm adding those diagonal entries. That is the trace, right, of A. And the product equals the determinant. So we'll try to use any of these if time permits on the next session to confirm our eigenvalues. So when we add our eigenvalues, we should get the sum of the trace of A. Now they say that the matrix is diagonalizable if and only if the sum of geometric multiplicities equals n. Right? Now, yeah, we'll come to that. Remember, this is an n by n matrix. Now, for verification methods, first we need to solve the determinant of A minus lambda I to be equal to 0. Then we find the eigenvectors. So first we find the eigenvalues. We do this, right? Solve the determinant of that. And then inside this equation, we're going to find the characteristic polynomial, right, inside this before we can find the lambdas. That equation you find there that you equate to 0, that is your characteristic polynomial. Sometimes they'll bring a question and they say find the characteristic polynomial. They want you to just find that equation, then you get those 3 marks, right? Then they say to find the eigenvectors for each lambda, solve this system and find a basis for null space. Remember, how do we, now the question will arrive, or we'll get to, how do we find the basis for a null space? We've been looking at how to find the basis before, but I'm going to do a revision for that, right? So now they say to check diagonalizability, ensure the number of linearly independent vectors equals to the dimension of V. Right, remember the dimension of V, this is the domain, given that V is equals to double O, right, in most cases. So the dimension of this should be equal to the number of linearly independent vectors. This is the simplest one to look, but we're not going to focus on one thing. We're going to look at as many as we can, right? Now, for the additional notes, eigenvalues determine the scaling factor of eigenvectors under T. This one is for people who are interested in some extra info, right? Non-diagonalizable matrices have at least one eigenvalue with geometric multiplicity less than the algebraic multiplicity. So these multiplicities, we'll look at them as we go on, right? Which one is the algebraic, which one is the geometric. Now, the first example, we're looking at these examples to find the eigenvalues. First thing that you do, so let me come here, right? Let me come here. So I'm just gonna open this. So we have two parts of this thing, right? Let me say, or let me just say diagonalization. And then we have this type of equations, right? Let me say to find the eigenvalues. So we have a minus lambda I. Remember, this a minus lambda I is coming from this. We have this, that lambda AV is equals to lambda V, right? But this is the same thing as having AV equals to lambda IV. You see, right? If we want to focus this thing on matrices only, because remember our vector is this one is the eigenvector. Our eigenvector is in the form of a matrix, right? Now, if I take this to the other side, I'm going to have AV minus lambda IV. It's also possible, remember you're not restricted, it's also possible to take this to the other side. So you can also have this. So I'm just writing this so that those who read other books and they find other methods, they see that they're all gonna take you to the same solution, right? Now, if I factor out V here, I'm going to have A minus lambda I V, which is equals to 0. And then this side, I'm going to have lambda I minus A V, which is equals to 0. Remember, a vector is always on the right hand side, right? Now, these two are always going to give us the same solution, guys. Reason being, if I factor out the negative here, remember I can drive this to this. If I factor out the negative here, it's going to be A minus lambda I V, which is equals to 0. And if I divide both sides by negative, they'll still take me here. You see, right? So wherever you'll be practicing this and you find that they're either using these two formulas, the first formula is this one, A minus lambda I equals to 0, will still give you the same solution as the determinant of lambda I minus A equals to 0. So it doesn't matter which one you use, but ourselves, we're going to use this one because it's much simpler, right? Now, we have this. Now we're given a question here. The first question, they say we should find the eigenvalues of A equals to 2300, right? 2300. So let's look at that. Now we are going to say, first we find this one, right? They say find remember there on the PDF I didn't put everything, right? Eigenvalues 4, so I'm gonna write all those things which are skipped here. 2003. Now for us to find this, first we need to find a minus lambda I, which this is equals to 2003 minus lambda, this is 1001, because we're dealing with a 2 by 2 matrix, right? Now this will just be 003 plus minus lambda 0 minus lambda, right? And this will give us 2 minus lambda 003 minus lambda. So this tells you that every time if you're using this formula, every time here you're just gonna come and subtract lambda on the diagonal entries only. You see, right? Now we have this, we come and find the determinant of a minus lambda I. The determinant of this will just be this times this. So I can just put it like this. I prefer this, right? Because sometimes it won't always be this easy. You need to apply methods. So this will just be 2 minus lambda 3 minus lambda minus 0 times 0, which this is equals to, now this is a 6, this is a minus 2, minus 3, it's minus 5, lambda plus lambda squared, this is 0. Now if I let the determinant of a minus lambda I to be equals to 0, that's when I can find the characteristic polynomial. You see, right? Now the characteristic polynomial is this: 5 lambda minus 5 lambda plus lambda squared equals to 0. But we should write it like this. Let me write it in this way. This is the polynomial, right? Now it comes now to say that we can now factorize this. We'll have lambda, this is minus 5, this is 6, it means that must have minus 6. So it's either you have this one here as positive or negative, or you can even have this 3 and 2. Remember these two, as long as they can give you this, right? So if I have minus 6 here and minus 1, since this is positive, so if it was negative, I could easily have minus 6 and 1. It could give me this one. Since it's positive, I'm forced to use 3 and 2. So you can use any means to find that. Remember, we have passed factorizing. Obviously, everyone knows how to factorize. Then this shows us that lambda is equals to 3 and lambda is equals to 2. Remember this condition that we had there. Does this other property, I think it was on the key properties. Let's say, let me see, I think it's the key properties. I was talking about the diagonal. I think maybe it's on the definition. Let me check. Yeah, the sum, yeah, it's on the theorems. The sum, let's say the sum of the eigenvalues equals the trace of A. Who can tell me, how do we find the trace of A? Anyone who has a clue, how do we find the trace of A? Remember, I've already told you how to find the trace of A, right? How do we find the trace of A? What do you do to a matrix if you want to find the trace of A? Guys, how do we find the trace of A? Here with the ghosts. How do you find the trace, guys? Oh, you forgot. Especially those who are doing SMTB, there's no way you might have forgotten. You guys always do this. I don't know about SMTH, but this year they're also doing it to find the trace. So here's how you're gonna find the trace, right? So you come to the original matrix, you add the diagonal entries. The trace is equals to 2 plus 3, which is 5. So I add this 2. So it's equals to 5. Now it says that the sum of the eigenvalues is equals to the trace of A, and indeed it's true. 2 plus 3 is what is 5, right? Now we know that the eigenvalues are 3 and 2. So you also need to conclude like this, right? Now let's see if we want to find the eigenvectors. For this question, right? For us to find the eigenvectors, we're going to consider each of these. We say for lambda equals to 3. Let's start with this one. We go back to this. We need this. You say, right? For lambda equals to 3, which is this. So we're going to say now A minus 3I will be equals to, remember this will just be, that matrix was 2 and 3 down there, right? So it's just going to be equals to 2 minus 3, 0, 0, 3 minus 3. So let's see that. Yeah. Now this is going to be minus 1, 0, 0, 0. Now we come and find the determinant. And we find that the determinant here is 0. So this is what I wanted to check, right? So when we do this, right, we find that the determinant is 0. Do we see this, right? Ne? So what I want us to check now here is this. If we come and say this, remember there was this formula from the beginning to say that AV is equals to lambda V. So the formula that we're going to use strictly for us to find the exact eigenvectors will be that we're going to have this. I remember at first we had something like this, right? If we take this to the other side, I said that you can take anywhere. But since we're already using this one, we're going to have A minus lambda V, which is equals to 0. So this is what we'll be using. You see, right? And remember this one was what? I erased that part. It was minus 1, 0, 0, 0. So this is, if I come and use for lambda equals to 3. So let me write it here. For lambda equals to 3, we're going to do this. We're going to say x2, and then we come and say this is A minus, this is, so that here we're going to use I, right? This pen is starting to misbehave. We need that I here. which will help us to be able to change this to matrices. Yeah, then we equate this to 0. Now we're going to use this formula always, right? We're just gonna plug our lambda there and so on. So it means that from here we can have, this is minus 1 0 0 0. I've already calculated this. We found minus 1 0 0, and then this is x1 x2, this is 0 0. Then we solve for this system. This is minus x1 plus 0 x2, which is equal to 0, which this implies that x1 is equal to 0. But we don't know what is x2, so we can just let x2 be equal to t. So it means that our v in this case is going to be equal to, so reason being we're letting x2, let's come back to here. This is x1, so this is the method that we'll be using, right? Our x1 has a leading 1. We can easily change this to a leading 1, right? Or yeah, then our x2 is a free variable, so we're always gonna let a free variable to be something t or s. So when I come here, our x1 we know it's 0, then our x2 is t, but we're interested in that constant, it's 1. You see, right? If I factor out the 2, I'm gonna get the 1. So it means that this would be our eigenvector for 3. Now we look at, we say for lambda equals to 2, let's say for lambda, remember before we had that this minus lambda I is equal to, it was 2 minus lambda 0 0 3 minus lambda. Then we just come and plug our 2 there. And this gives us 0 0 0 1. Then our free variable in this case, it's x1. So we're going to let x1 be equal to t. Then here we know that if I come and do this, if I come and use this equation of a, this one av is equal to, not av, let me just write it like this so we can save time. V is equal to 0. We're going to find this. We're going to find that this is, remember this is 0 0 0 1, and then this is x1 x2, which is equal to 0. And then we're going to have, this one is invalid, right? Let's not use it. Let's use this one. We're going to have x01 plus x2, which is equal to 0, which this implies that x2 is equal to 0, meaning that our v will be x1 x2, which we know that our x1 here it's t, so we're interested in that constant, right? The coefficient of t is 1, then this is 0. So we see that the eigen vectors here are, so let me conclude and say that the eigen vectors are 1 0 and we started with 0 1 and 1 0. You see, right? These are the eigenvectors. Now we have this. We have two eigenvectors or eigenvalues. We have two eigenvalues and we have two eigenvectors. And we're in a 2 by 2 matrix. What does this tell us about A? So here we can easily say this. We can easily use this condition. What does this tell us about A? Is it diagonalizable or not? Yes or no? Is A diagonalizable? Yes or no? So if we go back, we can check that condition. We say that we can check like that, right? So let me go back to that condition. The condition is, it's here. It's number 3. That's this point here. We can look at this point and also this point. Remember here, this point says that eigenvectors corresponding to distinct eigenvalues are linearly independent. So obviously there we saw that we have two eigenvalues, and each of those has its own eigenvector. So it means that they are linearly independent, right? So they can ask you, sometimes they can give you the matrix and say, check if these eigenvectors are linearly independent or not. So that's how you're going to check. Just going to check if they all have their own eigenvectors. So now this point says that if we're in a n by n matrix, let's say in this case we're in a 2 by 2 matrix. If we're in a 2 by 2 matrix, we're going to say that T is diagonalizable if it has n linearly independent. This is our n. Remember, our n is 2. And indeed it has 2 linearly independent eigenvectors. So it means that that matrix is diagonalizable. You say right. So we can use any of these conditions. So let's go back now and check. So we got the eigenvectors to be 2, 2. Let me check the eigenvectors. We got the eigenvalues to be 2, 2. And these are the eigenvectors. So I only found for 1. I only checked for 2 here. So that's why I said that here I only included few information, right? So we see now you see how I got this. The eigenvector for lambda equals to 2, right? Then I also did for 3. I got 0, 1. So now let's look at the second question. The second question, they say find the eigenvalues of A, which is equals to 1, 1, 1, 0. Okay, I think we also need to look at the diagonalize for that one. Yeah, check here. Is A diagonalizable? Yes, it is, because there are 2 distinct eigenvalues, you see right now, and 2 linearly independent vectors which are diagonalizable. So we have checked that. And just that here I didn't include that we're in a 2 by 2 matrix because we can easily see that, right? So I should have also included that, and we're in a 2 by 2 matrix. So this is indeed diagonalizable. Do we see this? So now let's check the second one. The second one, they say we're given 1, 1, 1, 0. So they say we must find the eigenvalues. Now pay attention. If you were lost on the first one, make sure to pay attention on this one, right? And they say A is equals to 1, 1, 1, 0. And they say we should find the eigenvalues. So let me say to find which this, I think it's this screen, because the pen is doing other things. To find eigenvalues. So remember, for us to find eigenvalues, now I'm going to skip all the other steps I was using, right? You can easily start here. Determinant of A minus lambda I, which this is also the determinant. So let's check. Determinant of this minus lambda I, it's also this. It's a 1 minus lambda. See that you're just going to come there on the diagonal entries and subtract lambda. You say right? And this is equals to 1 minus lambda, 1 minus lambda, minus 0, 1. And this gives us 1 minus lambda squared. You say right? Which is the same thing if I try to expand it. I'm going to get 1 minus 2 lambda plus lambda squared. And if I come and let the determinant of A minus lambda I to be equals to 0, then I'm going to get this. Lambda squared minus 2 lambda plus 1 to be equals to 0, which we know that this is the characteristic polynomial. Right? Now, we can try to factorize that if it's possible, but already it's possible, we know from here, right? We know that we're going to get lambda is equals to 1 and lambda equals 1. You see, right? Now, when we get lambda equals to 1 and lambda equals to 1, what does this tell us? We have let me go back to here. We have this. They say that a matrix is diagonalizable if the algebraic multiplicity. Already now we're somewhere we're looking at the multiplicity, right? Now we have algebraic multiplicity and the geometric multiplicity. Can we try? Let's take 30 seconds, right? I'll be back now. Take 30 seconds and then you think which one is the algebraic multiplicity and which one is the geometric multiplicity here. Or what is the geometric and what is the algebraic? Let's start with the algebraic. Let me just write them here, right? Algebraic and geometric. Yeah, let's think about that. Yeah, so is there anyone with the solution to this? What is the algebraic multiplicity? What do we look at if we're looking for this? And what do we look at if we're looking for this? So now if we check the algebraic multiplicity, right? This one, the algebraic, we're going to be looking at the number of, actually let me say the number of these eigenvectors, your eigenvalues. This one will look at the number of eigenvalues. Then this one, the geometric, will look at the number of linearly independent. This one is the number of eigenvalues that are repeating, right? That are the same. So this one, the number of linearly independent vectors. So meaning that here we're looking at eigenvectors. So you should know this. Algebraic, you look at eigenvalues. Geometric, you look at eigenvectors. Now this tells us that here we have two which are repeating, is the same thing which is repeating, right? It means that the algebraic multiplicity is 2. Then the geometric, we need to find the eigenvector for us to know the geometric. So let's go and find the eigenvector for 1. Already, if we come there, we remember we had, we must have something like this. The formula was like this. So, meaning that lambda is going to be 1, right? Now this will be, this is, oh, it was 1, 1. Our matrix A was 1, 1, 1, 0. So this is going to be 1 minus 1. There's 1, 0, 1 minus 1. So this is what we're going to do. And then this will be just x1, x2. So this will be 0, 1, 0, 0, x1, x2. Now this is, we're only going to look at this, right? It's a 0, x1 plus x2 equals 0. So if I do multiplication there, then I add them, I equate them to this 0, I'm getting that. So this tells us that x2 is equals to 0, right? Now, since we got that x2 is equals to 0, x1 we don't know what it is because it's a free variable, so we're just going to let it to be t. This is x1, x2. So we're going to let x1 to be equals to t, meaning that our eigenvector will be, our x1 is t, so I'm just going to have 1 there. Then our x2 is 0. So this will be the eigenvector. So that will be the eigenvector. So how many eigenvectors did we find? The linearly independent. Obviously, we know that this is linearly independent, right? How many linearly independent eigenvector did we find? 1. So it means that our geometric multiplicity will be 1. So remember, they say that if this is equal to this, therefore this is diagonalizable, right? So let's go back and check that. They say that they say that a matrix is diagonalizable if the algebraic multiplicity equals to the geometric multiplicity for all eigenvectors, or for all eigenvalues. But here they are not. 2 is not equal to 1, you see right now. So it means that if we come and check, so let's start by checking our value, or eigenvalue is 1, and the algebraic multiplicity is 2 because there are 2 of these ones, right? Now we look at the eigenvector. So I made sure that I do each example the same thing. I find the eigenvalue, eigenvector. So they said find for this 1 free variable. V1 is free variable, right? Is this one. Should have let it to be t. I think I made the mistake when I was stepping. It's supposed to be 1 0, so we can just correct that. This one's supposed to be 1 0. So they say that the eigenvector is, so this one is supposed to be t, this one, and then this one is 0. Now this is what we're going to be having, and the geometric multiplicity is 1. You see that, right? Now if we come and look at the diagonalizable, if we're going to check if this is diagonalizable, yes or no, the algebraic multiplicity is 2 and the geometric is 1, hence this is not diagonalizable. You see, right? So you're always going to have different types of reasons for you to say this. And for this one, number 3, I did put this on purpose. Here you're going to find that you're going to get something like root of minus 1. Plus or minus root of minus 1. This tells us, remember this in complex numbers, this is plus or minus I. So we get positive I and minus I. Since these are no real eigenvectors, this won't be diagonalizable. Every time you get something like this, you need to come to this conclusion to say that these are not real. There are no real eigenvectors for this. Right, so this wouldn't be diagonalizable. And then this one we had eigenvalues 2 and 3, which are 2 linearly independent vectors, meaning that they all had separate vectors, right? It means that it's gonna be diagonalizable, which is the same thing we used here. So if we check the reasoning, we are just gonna revolve around these 3. This is 3 multiplicity and 2 geometric multiplicity, which is not diagonalizable. Then this one had 2 vectors and they're linearly independent, diagonalizable, 2 linearly independent. Like that, you see, right? 3 distinct values, 3 linearly independent eigenvectors. Doesn't matter how you put it, as long as you specify that there are 3 eigenvalues, or you just write them like here, right? Then you specify that there are 2 linearly independent, or if there are 2 eigenvalues, there should be 2 linearly independent eigenvectors, right? Just like that. If you can check the reasoning, guys, they revolve around the same thing. You see, right? If you can check. Now this one, we're able to find 2 eigenvalues over complex number, as I say that. So when we come and do these problems, your reasoning, whenever you look at diagonalizable matrix, your reasoning should revolve around those. You see, those 3. You should try to check what type of a reasoning can I have here. You see, right? Your reasoning should be somewhere close. Now let's look at this. There was a condition that said that our eigenvalues, the sum of the eigenvalues is going to be equal to the the trace. If we check this, what is the trace for this? Is 0 plus 0. You see, right? That's why here we couldn't get any real values. We got I and minus I. Then just that I've never tried if this thing is really true for all. But if you can check this, 4 plus 1, 2 plus 3 is 5. You see, this is 5. The trace is 5. This is 5. And then here, the trace is 0. The eigenvalue is 0. You see, right? Now, on this one, the trace is 2. Then the eigenvalues are 3 and negative 1, which means that there are 2, right? If you check, the trace is 2. Here the trace is 1, is 5 plus minus 4, yeah, it's 1. Then here the eigenvalues, we got 3 and minus 2, which sometimes I said that it's not always the case, right? Then this one we got what? If we add this, we get 7. If you check here, we got 1, 2, 3. You see that it won't always be the case, but in most cases it's gonna help you to check, right? Usually it won't be the case with bigger values most of the times, but if it's these small values, and mostly it's always the case. So we can check that. So any question, guys? If you have no question, it means that we can stop here. Please try to do that, the problem set here. You can try to do the problem set. And then you also try to search, right? Remember we said that the sum of the eigenvalues is equal to the trace, right? So you can try to check. Let me see. I think for these ones, did I do the sum correctly here? Yeah, it's correct, man. I mean, I was doing the sum incorrectly. This is 1. The trace here gives us 1, right? This also gives us 1. This one gives us 7. The sum of this 1 plus 2 plus 3 is it 7? No, it's 6. This one. Also, the sum here is 6. Let me see, here it's 0. If we add these 2, we get a 0. And then the sum here, it's 6. If we add these 2, we get 6. Yeah, I think it will always be true. I think I lost my mind a bit there. Then I started doing wrong calculations. Yeah, so you can always confirm like that, right? So I think all that I have here, they're always true like that. So you can always confirm if your eigenvalues are correct by finding the trace. So I think the first thing we can do is find the trace. Then once your trace works out, then you're good to go. You already know what number of eigenvalues are you looking for, or what is the sum of your eigenvalues. Then you know that you're correct.